Welcome back to our Center for AI Innovations seminars series again. Today, we are very happy to have Janice McMahon from Lucata to give us a presentation about some of the exciting work that the company is working on actually delivering in terms of the engine for running very large graph-based computations. So Janice has her undergraduate and graduate degrees in electrical engineering from MIT. She has been a software professional since then in the high performance and massively parallel computing markets since her graduation for 30 years or so, working on all kinds of interesting technologies, ranging from radar and sonar real-time signal processing systems to the performing application analysis for a variety of application areas, and sort of figuring out how to make these applications to work best on the specialized hardware. She worked for research institutes, defense contractors, and computer vendor startups. So this is kind of very exciting to see such a sort of a broad spectrum of applications and technologies and places that she worked at. Throughout her career, she worked as an implementer, an application mapping analyst, a project manager, customer support engineer, and the researcher. And so she has worked on compilation, algorithm mapping, and performance analysis for Lucata architecture since 2012. So that's her biography. We are really looking forward to learning more about this graph engine that is capable to run graph-based problems which are beyond the reach of today's platforms. So Janice, please take it from here.
Alrighty, thank you so much, Vlad, for the introduction, and thank you everybody for having me today. As I mentioned, I think I'm going to turn off my video, at least I think I am, for bandwidth. So let me just do that, and then I'll jump right into it. So I'm going to talk today about graph processing and migrating threads, and I will explain what I mean by all of that as we go along. The Lucata architecture and some of the problems that it's good at. As Vlad mentioned, I've been associated with the technology since 2012, and it's gone through a lot of iterations, and I've gone through a lot of relationships with it. So my perspective is sort of broad, but please stop me if there are any questions at any time. Okay. Alrighty, so what is the Lucata mission? Just to back up, what we're providing is a fundamentally new solution to identify relationships within large unstructured data sets. What does that really mean? Large graph database problems, from our point of view, they typically, well, the graphs are large, so they're distributed over many memories. Data movement dominates the performance, not computation. And the memory accesses, and this is fundamental, they're irregular, remote, and unpredictable. And I'm going to talk a little bit more in more detail about what I mean by that. The other side of things, from the other piece of the picture from our perspective, is that traditional systems are going to fail. And the reason is primarily because of caches. A cache is designed around the idea to exploit locality, but the large data graph problems we're talking about don't have that locality, so memory caches are going to break down. Interconnect bandwidth isn't sufficient, and then because of all of that, the power consumption is very, very high. So this architecture was designed a while ago, but has gone through many iterations to meet these needs, and we call it the context flow architecture. I'm going to make a little bit clearer exactly why we call it that. So just to talk about the space that we're interested in, as Vlad mentioned, I've worked in a lot of different spaces in my career, signal and image, and as well as now the analytics world. And these problems have different structures. So, and the benchmarks that are listed here sort of reflect that structure. When you talk about, I don't know, starting, I guess, in the 70s, you're talking about LinPack. You have these dense matrix problems, and hence you have conventional systems designed around that with caches. And conventional systems get very, very high efficiency on those types of problems, and we do as well. We get very high efficiency, as you can see in the chart there. But if you look at some of these other applications as represented by the benchmarks listed here, the random updates benchmark, the conjugate gradient, sparse matrix operations, graph operations, and then I don't know if people have heard of the fire hose benchmark, which is sort of a security benchmark, finding events and streams of data and things like connected components. Conventional architectures don't do well on these applications. And for the reasons I mentioned before, we have the interconnect problem, we have the cache problem. So you typically see less than 10% efficiency or of peak performance in these architectures. And what we're designed to do is do much, much better than that. And as you can see from the chart, in some cases, we actually do get over 90% on some of these applications. We don't really get lower than 50. So that's the kind of thing that we're trying to do. So what is the context flow architecture? And so the pictures sort of show the example here. What we're basically doing is moving the thread on a remote memory access. So when a thread in a processor associated with the memory makes a remote memory access, it triggers in the hardware a movement of that thread context to the destination. So you can see here on the top, if processor 1 makes it a reference to processor 3, then processor 2, then processor 4, the actual thread context, which is small, moves to the locale of the data being accessed. And this is in contrast to a conventional computer. On the bottom, you see a typical message passing scenario here, where the same types of references involve multiple round trips. You've got to send a read request, you've got to get an acknowledgement, then you've got to send a read response, and then an acknowledgement. And typically, those are on the order of cache lines, so they're bigger. They're larger messages in each transaction. So not only are there more transactions, they're larger ones. By migrating the context, it's a one-way trip. So you don't have as many you don't need an acknowledgement. It's a very lightweight thread managed in hardware. You don't need an acknowledgement. So you have a one-way trip here, and it's much smaller. The thread context is much, much smaller. And we'll talk a little bit later about why. So you have less data, move shorter distances. It's managed in hardware, invisible to the programmer. The programmer does not worry about it at all. The processor's utilization is higher. The network protocol can be simpler because you don't need all these acknowledgements for the data you're sending. And because of all of the reduced data movement, you have the lower energy cost and much higher efficiency on the types of problems we're talking about. So this enables the kinds of fine-grained parallelism and high scalability that you want to see on the graph problems that you see in data analytics. So we see it as an enabler for this whole new problem space that's emerging. Okay, so let's talk a little bit about graph algorithms and what is the structure of these problems. This might be a review for some of you who are working in this area, but the graph data structure is you have a set of vertices, and then you have a set of edges between them. Each vertex is an entity in a problem. It represents something, maybe web pages or people in a scenario, and then each edge denotes a relationship between those entities. So extracting information from the graph means you access numbers according to the pattern of the graph. For example, if you're on one node here, and then you want to move to an adjacent node, that's data dependent. It's going to depend on what the relationships are between the nodes, and you don't know that a priori. It's not like a signal processing problem with a matrix where you know what the structure of it is. So we call that traversing the graph, when you start with a node and then you basically follow links in some pattern to get an answer to a problem that you're posing with respect to this data structure. So you're basically querying the data structure to ask a question, and answering the question means that you have to travel between nodes along links in some pattern that you don't know a priori, or rather you know the pattern, but you don't know what the access will be because you don't know what the structure of the graph is. So the fundamental question in a distributed memory system is, how do we partition and store the graph in a manner in which we can still get high performance? In other words, we want to minimize the impact of all this data movement on the algorithm performance. i.e. we want the high efficiency and we want to get, maximize the computational hardware in the system. And this is a question that you ask at every level of the memory hierarchy. You could ask it between nodes. You could ask it between memory banks within a node. You could ask it between servers. The answers, of course, are going to be different because the bandwidths and the overheads are different, but the question is the same. How do we partition the graph? How do we store it to get good performance? So one way you can think about it is you can do some kind of block partitioning where you can arrange the vertices into blocks of memory, and then you store the edges, which is basically an index, into the children or the adjacent vertices. You store them in the same memory block as the vertex, and so traversing the graph. Again, it depends on the pattern. You'll have a lot of local references, but then you're going to have some that jump between nodes because your adjacent nodes may not be in the same memory block as your source node. But another main point here is that you're not doing generally large accesses here. If each node is a small chunk of memory, there'll be an address and maybe some information associated with that node, but it's still quite small. So you're accessing small blocks of memory as you traverse the graph in very possibly non-regular ways. And that, again, complicates any architecture that's based on caching and locality. So it's going to be the bottom line is it's going to be very inefficient for caches because there's little reuse, and there's going to be a lot of network traffic because you have the data structure distributed over multiple memories. So what is our performance advantage? The idea behind the migrating threads or the context flow architecture is that you reduce this network traffic by avoiding, as I mentioned before, the round-trip memory access. Simultaneously, you have, instead of a large block memory access, you have narrow channel memory, meaning every access to memory actually brings you a smaller word than a cache line, for example. So you improve your memory efficiency by not reading what you don't need to read, which is what happens in a caching architecture. You read a whole bunch of stuff, and if it's local accesses, then it's worth it. But here you don't have a lot of locality, so you're doing a lot of unnecessary data movement. So the idea here is to offer a huge performance advantage for problems with this structure, of which graph algorithms are a large portion of that class of algorithms. So, what are the application areas? There are a lot of them, and anywhere you have relationships between entities in a world. So, social, you can imagine web pages or social group analysis. Some large ones in the financial world, credit card fraud. This is a huge one, very devastating for companies. And so they put a lot of money into trying to avoid that. And graph algorithms play a great role there. Money laundering, malware detection. And then secondly, I mentioned the social world, identifying communities, which could be bad actors. If somebody is bad and he associates with a lot of other people, then maybe they're bad too. So this kind of thing you can imagine is very, very big in the defense community. But in the world of social media, recommendation engines, for example, if you like this and you're associated with somebody, they might like it too. That kind of, you can just see how that's all very nicely encapsulated in a graph. And yet completely unstructured. You don't know what the relationships are going to be. Insider trading, and then trend detection and security price movements. These are all the kinds of things that are going on in the world of graph algorithms. And what's happening now in the community is the graphs are getting bigger. The problems are getting more complicated. The graphs are getting bigger, and conventional architectures are starting to run into what we call the memory wall. Their memory architectures just can't support what needs to be done as the data structures get really big and as the number of entities in your problem get big, which is what's happening in the world today. So this is where we're going to shine with these applications with really, really large graphs. They're sparse, so maybe they have a lot of nodes, but they don't have as many edges. And then they have real-time constraints. So they need this, they need the high performance and the low latency on their problems. So this is where we're targeting our technology and where we're working today with the community to find the applications. So what are some of the, briefly, some of the software packages that do this stuff? There was a standards committee formed, I guess it was first presented in 2013. The committee was probably founded earlier. There's a seminal work in the duality between graph problems and sparse matrix algebra. It turns out you can express things like breadth first search, which is a typical graph algorithm, as a sparse matrix multiplication. That made it extremely powerful because we know how to express matrices, certainly, and we even know to a certain extent how to optimize them in a library. That's what LinPack is, basically. It's a big matrix library. So the idea was to come up with a standard and a set of building blocks that the community can use for graph algorithms that would, number one, allow for high expressivity, and then number two, allow you to work on the performance of those primitives to get performance on the application independently of expressing the algorithm. So the community could go away and develop algorithms using this software, and then the architecture community could go away and optimize the library, and they could work independently, and then the end result, you get a lot of graph problems with very high performance. So this was presented at the High Performance Extreme Computing Workshop in 2013, and it's got quite, as you can see here, quite a number of top-notch academic and industry representatives working on this. So it's pretty comprehensive. Again, this is just the people that are involved. Lincoln Labs was probably one of the seminal. They really sort of kicked it off, and you know, large number of very top-notch researchers working on it here. So what are the primitives? And it turns out you don't need a lot of primitives to express this stuff. You've got your basic matrix vector, matrix multiplication, and that basically is a traversal of the graph. You have element-wise operations, and again, a lot of this borrows from MATLAB, kind of. In fact, it's very closely tied to MATLAB. Your basic extractions and assigns and applications, reductions, transpose. These are all very typical things. So you don't really need a lot of primitives here in the sense that to specify a complex graph algorithm. There is, however, a huge amount of complexity in this library. It's based on semi-rings. So there's like thousands of semi-rings that you can, it turns out, and hundreds and hundreds of operations. Because what this does is it abstracts the operations, the fundamental operations from the sort of macro operations. So it's extremely, there are a low number of primitives listed here, but it turns out there's a huge coverage of algorithms in the space that the library covers. So you can build really, really complex graph algorithms in this type of library. So what's available in the community today? There are reference implementations. The SuiteSparse is sort of the gold standard, and you can get that free. I don't think I have an actual link in this talk, but I can certainly get you one. IBM has a high performance implementation. There are a lot of projects out in the industry using this library. They're MPI based, Java based. It's very tied to MATLAB already, but there's even more going on. There's a C++, the SuiteSparse standard libraries is C. There's a C++ template library being developed. That's out of SEI actually. And then there's the Texas A&M is doing the SuiteSparse, which is the standard implementation. And then there are other efforts going on. What's interesting about this library is it turns out to be very high performance. So it's getting out there. In fact, the Redis graph database is actually built on top of GraphBLAS. So if you go, what that means for us is if we go away and make GraphBLAS run very quickly, we kind of get to first order a graph database for free in a sense. So we think it's a very, very powerful underneath the hood kind of technology. So this gives you an idea of what the performance is. On a single-threaded performance is already doing faster than pure MATLAB, factors of about 2 to 8. On parallel-threaded performance, it's much faster, like 60 to 120. And these results, by the way, it's 2019, so they may actually have already improved these. But we see it as rapidly gaining traction in the community and perfect for us, because we can go away and, we're a small company, we can go away and implement this library and then kind of ideally get a lot of things for free. And because it's based on sparse matrices, we should do very well on it. Quickly to talk about graph databases. What is a graph database? It's basically a database built around a graph structure. So you make queries to the graph instead of doing SQL type relational queries. So the nodes are indexed for fast lookup. You have a property graph that encapsulates the properties of all of the entities in your database. You have uniquely identified nodes for the objects in your database, and edges, as we mentioned, denote relationships. And then each edge has a label that defines a relationship. So comparing with a relational database, you have a lot of flexibility. You can have very dynamic relationships in the graph just by simply adding nodes and edges. The querying is more intuitive for a lot of these types of problems. The graph is a much more intuitive data structure. And then certain operations are just going to work better. However, graph databases are not a panacea. They're not always the thing that you want to use. And also, there's no nice unified query language like SQL. Everybody knows SQL. Everybody uses it. There's nothing like the SQL analog in the graph world. So some sample results. I don't want to go into a lot of detail, but basically you get a lot better performance on certain queries with the graph database. And you also get good scalability as the problems get bigger, as the machines get bigger. The efficiency stays good there with the graph database as opposed to a relational database. There are a number of these commercial graph databases out there. Tiger DB is, and Redis Graph and Neo4j are the three biggest competitors, and we're sort of looking at all three. We're just the substrate upon which it'll be implemented. So we're not, we don't have a bias towards any one. I mean, we could work with all three. But as I mentioned, Redis Graph uses GraphBLAS. So when we have our GraphBLAS ready, we'll kind of get that one. And then we're also looking at these other ones too. And each one has a strength in the market. And we're interested in all three. So switching focus a little bit, I've talked a lot about graphs, the structure of graphs, the applications, the algorithms, the software that is out there, and why it's important. I'm going to switch gears a little bit and talk about our architecture. And I've just told you that we're going to be really efficient and good at graphs and why that's important. Now let's talk about how we're actually going to do that. And so I'm switching. So all you folks that were graph algorithm centric can change, and all you architecture folks can now have your time. So this is our node architecture here. Basically, each node is a shared memory multiprocessor itself. So you have a cluster of Lucata compute elements, that yellow box there. This is again within a node, and each node also has some number of these LCs, and also has some number of DRAM banks, and I'll have exact numbers later. And each bank of DRAM is a memory bank that has a memory side processor and a controller associated with it. And what does that mean? What that means is we've got these little processing units that do atomic, simple operations, and they're attached directly to the memory. So if any of you have heard of PIM, processor and memory, or compute and memory type architectures, that's this side of it. There's a little processor attached to every memory bank that can do quick stuff like additions or min max, and we're expanding that all of the time. But And the idea there is to offload some of that processing from the compute elements, and again, to get higher efficiency for these types of applications. So all this stuff, and you see other stuff on the slide, network interfaces, and then interfaces to a server. All this stuff is connected within a node by a stacked ring on-chip fabric. Again, very fast, and so local accesses within a node just kind of happen. You know, if a compute element accesses a memory bank within the same node, it just happens within this stacked ring architecture. Each node has a run queue of threads, and we have lots and lots of threads you can run in a node. You can have over 1,000 threads executing in a node at a time, either queued up in the run queue or actually executing in the compute elements. And then we also support parallelism, parallel file sets, and parallel data ingest. So all of these compute elements are sort of managed by a server here. So we're integrating with standard x86 front-end servers. And server is a little bit of it denotes something it's a little bit more than just a server. Basically, Linux is running on the x86 architecture. So what happens is when one of these compute elements wants to do a system service, that's where it does it, on this x86 server, and it goes into the service exception queue that you see in DRAM there, and then goes out to a server to be executed. So if you have a printf in your code, or if you have a exception or another system service, it's going to be done on the x86 server. And the beauty of that is we kind of get Linux just by having that there. So we can save all the computationally intense stuff for the compute elements, and then whenever we need Linux stuff, we can go out to this server. So our processors can be very simple and very high throughput on the operations that are important. But we get the benefit of a standard Linux environment with everything that comes with that, including software and what's underneath in the system. So this is really powerful. It enables us to get, as I said, the benefits of Linux, but still get the high performance where we need it on our algorithms. So each node has SSD associated with it as well. So its own disk that looks like an independent disk, but we have libraries and tools that allow you to look at that turn that sort of a little bit into a kind of local cache as well. Each node has two networked interfaces to a high bandwidth, high radix network, all of the nodes are connected by this network. So what happens here is when one of my compute elements makes that remote address, that access to a remote memory on another node, the hardware packages up the thread context and it sends it out over this high bandwidth, high radix network. Once it's sent out over the network, it goes into the run queue of the remote node, and then execution just proceeds as if nothing happened. And the programmer never even needs to know about that. And the reason that works is you have actually kind of like a SPMD, or single program multiple data model, where every node has a copy of the same program. So you don't need to send code out over this network. You really send a program counter, essentially a program counter and a set of registers, and that's enough for for basically the process to just continue on the remote node. So quickly, just to talk about performance, since I highlighted scalability, this shows you where we are right now with two very important graph algorithms: breadth first search and the k-hop algorithm, which is basically finding all of the nodes in a graph that are k hops away from a source node. And you can kind of see from these, this shows you one chassis, two chassis, four chassis. I'll explain that later, but it shows you some pretty good scalability results here. As the x-axis is scale, graph size, and then its edges traversed per second on the y-axis. As you can see here, as the graph size goes up, we're getting more and more edges traversed per second. And we're also getting improvements as you increase up the machine size from 1 chassis up to 4 chassis. And these are recent results, and these are being improved every day. I'm not even sure these are the most recent results. This is from our website. So I think we even have better results than this. So what is the system that we're selling today? It's our compute nodes combined with that x86 server. As I mentioned, easy integration with standard software and easy porting of applications. We have a wide variety of memory storage and networking options. Each chassis is 16 nodes. There are 64 nodes per rack and up to 64K nodes per system, which is a large system. We have lots of memory per node with a lot of options. And then the system interconnect is 200 gigabytes per second per node. So that's what's supporting the migration of the threads there. So what's shown in the picture is 1 chassis. You can get 8 of these chassis into a rack, and then you can scale the system up to 64K nodes total. So to touch briefly on I/O, per node, what we're designing toward is 8 gigabytes per second, and you can have up to 256 parallel streams. And again, this assumes 1 PCIe SSD per node, and this is pretty amazing performance in itself, given the compute to I/O ratio here. And then if you're talking about network I/O, bandwidth 12.5 gigabytes per second, transaction rate 97 mega transactions per second, and then ingest rate as shown 1.2 gigabytes per second. And again, that assumes a 100 gigabyte NIC and 64 byte packets. Data ingest and I/O is extremely important to these systems. In addition to the random access and the memory patterns of the graph, modern applications will be requiring you to update that graph. Data comes in and you either have a new vertex in the graph, or you have a new edge, a new relationship, or there are deletions. So you need to be able to support high rates of I/O for the graph applications of the future. And this is a key point of our architecture, is that we can provide this kind of bandwidth, the kind of bandwidth that is going to support these future applications for very, very large graphs. So how do you program it, which is a key question for most people. So we do have a native shared memory programming model, and that's what's going to get you the most performance and flexibility. And basically what that is, it's a C++ based, with standard libraries based system. And we have support for parallelism, concurrency, and data distribution. And the way that works is we use the Silk scheme for multi-threading, which supports dynamic multi-threading with high performance. So we spawn a thread, we can synchronize threads, and then we can do loops. So there's really just a couple of primitives that you add to your C code to support the kinds of parallelism that we're doing with multi-threading. For data distribution, we have our own library that allows you to just distribute data over the nodes. And it supports both block and cyclic mappings of data, and it's fairly easy to use. So we don't require that you do a lot to distribute your data. And then once you've distributed your data, accessing your data is really as simple as a C array access. And underneath the hood, the system does all of the migration and everything independently of, transparently to the programmer. So that's our native programming model. And that's going to give you the highest performance. And that's because you lay out the data yourself, and then you manage your own concurrency and you sync your own threads. We also are looking at higher level software that runs on the x86 server and then uses a Lucata driver to actually execute on the cores. So things like Python and higher level C++ codes will use this kind of model where you know, all of that concurrency and data distribution is done at a lower level. And then all the programmer needs to do on the x86 server is run this higher level language, and that will use the driver to go through it and actually execute on the cores. So there are a number of ways that you can program this thing. Right now, most of our development is done in C, C++ with Silk primitives. We also have GraphBLAS. I'm going to talk about a little bit about that in a minute. So that's how you get your biggest performance, but you do have higher level software if you want it, and a means of accessing that performance at a lower level. So this is kind of another way of stating what I just said, which is basically there are multiple ways you can think about programming this thing. Greatest performance means you actually write a lot of code using our proprietary or C++ Silk and our libraries, and that's a great chunk of the code that you write. And so on the top level, it's really more just an interface. However, you know, there are modes where you can program at the higher level and then just use libraries directly and not have to implement any code on our machine. And then something we're looking at in the future, on the left there, the least programming effort is everything is done at a very high level language, and underneath the hood there's a database that does everything, and then that database uses the lower level of a Lucata API. So dynamic parallelism versus via Silk, I mentioned that. There are three key words for those of you familiar with Silk. There's Silk spawn, Silk sync, and then Silk for, which is a loop. So the Silk spawn just spawns a thread within the queue of a node, and then Silk sync just says basically everything that I've spawned needs to finish before you can go on. And it's pretty simple. You spawn a function, and everything is handled underneath the hood of creating the new thread and initializing the environment. We have libraries for distributing data. Our library is called Memory Web. We also have these intrinsic functions for architecture-specific things, and a lot of these have to do with there are different categories. Some of them are accessing machine state, like what's my thread number, what's my node ID, that kind of thing. We also have intrinsics that implement the memory side processing functions that I talked about. What happens here is the compiler just recognizes these special functions and knows that they're done using architecture-specific operations. Basically, they trap down to assembly and machine code. So again, it's a way of having something that's relatively easy to use. It just fits right into looks like a function call inside of your C code, but underneath the hood, it accesses some very architecture-specific stuff. We have something called replicated variables, because if you think about it, if you have a large distributed memory system, what do you do with constants? You don't want to have your threads all banging on the same node to access a constant. So we replicate the constant, which means that a version of it exists in every node, so that there are no migrations outside of the node just to get something that's the same for every node. So libraries, we have GraphBLAS I talked about. We have our own library called bdrill, which implements a lot of the common graph algorithms. We also have something called LA-graph, which is associated with GraphBLAS, which is a library of graph algorithms. So our GraphBLAS library, since I talked so much about GraphBLAS, it implements the full GraphBLAS API. And I talked about the operations. Imagine if you've ever seen a breadth first search code, or you can imagine writing a code that traverses a graph. You can replace that literally with one line of GraphBLAS code that just does a sparse matrix multiply, and that is your breadth first search. So it hugely improves the development time. And so your coding effort is very small. It's open source. It's written in OpenSilk, which is an open standard for Silk. And we're getting pretty good performance on that. Now we've also got Redis Graph, which is running on top of the GraphBLAS, and we've actually got this running on our architecture as well. Redis itself provides a huge performance gain over traditional Redis and also software-only competitors. So we hope to kind of ride that one by providing a very high-performance GraphBLAS that basically we can run Redis Graph for free. So the idea here in database terms is we don't have to shard the graph in order to process larger graphs, and that's hugely strong in the community. There's a lot of effort put into sharding that we just simply don't have to do because we can process larger graphs. Also in the architecture, part of the intrinsics that do the architecture specific things are access to performance counters. So we have a wide variety of hardware counters that measure performance parameters of the system. We can look at things like instructions per cycle, memory transactions, networks, stalls, and numbers of active threads. And this is extremely powerful if you're debugging an algorithm. And I talked about the different programming models. This is an example of something that you'd use at the lowest programming model where you're getting the highest efficiency for the maximum effort. And you're really, really worrying about the stuff that happens on the architecture. We have a simulator available. So typically that's where you start developing algorithms, on the simulator, and the simulator and the hardware have identical counters. So there's a pretty good match there. If you develop something on the simulator, you have a pretty good confidence that it's going to work and work to performance levels on the hardware. There are a lot of, you can start and stop counters for various sections of your code. So we have a lot of flexibility with that. And then we also have a lot of, we have a pretty strong set of profiling and visualization modes where you can see, for example, active threads is shown on the top there. So you can see the different colors are different node lists. So you can see there's a good load balance for that code and a good availability or good resource usage of the nodes. That bottom chart there is showing you basically migrations. And this is a new thing. I mean, our architecture, the Lucata architecture, is the only one that does to date this migration idea. So this is a whole new way of thinking about your problem. You need to worry about not only utilization of your nodes, but where are the migrations? Where are the threads moving? And it's really important to know that because this stuff is very dynamic. It's very data dependent. You're not going to know it a priori. And you can't plan for it since you don't know it. You don't know the structure of the graph. You can't plan where these migrations are going to happen. So the ability to run your code and then take a look at it and say, oh, I have a lot of migrations over there. What's going on? And then you use our library to play with different data layouts and see if there were fewer migrations with a different layout. Or that's extremely powerful and necessary for our architecture because you cannot map it out in advance. It's not like a signal processing or a dense matrix application where you can block it out and then you know what the access pattern is. You don't know here. So, we offer a lot of these visualization tools that allow you to look at things in that way so that you can optimize your performance. So there's a lot of detail in the next few slides about I/O and how it works. It's new to our architecture. It's coming out in the, we'll be shipping this spring and this will be included. But it's a pretty strong feature of our architecture. So it's worth talking about a bit. This shows you basically how it works here. I/O operations are initiated in that x86 server that I talked about. Basically, they are sent down through a PCIe switch. Into Pathfinder memory. The SSD that is on each node is used, and then the compute elements talk directly to the memory on a node. And in addition, the PCIe also talks to a network card. So the blue lines represent data transfers, and the black lines are basically control. And the point here is that you don't have any data that needs to go between the Lucata node board and the server. The server sends control messages, and control messages are sent through the switch, but the data goes directly from the network card into Pathfinder memory, into SSD on the node, wherever it needs to go, without any data needing to be moved between the server and the node. And this is really powerful here because it means that we can get lots of data coming in over the network in parallel, because this is going on in every node in the system, and we can have up to 64K nodes in the system. So this is what enables us to get this really, really high bandwidth I/O to support data ingest for these huge graph databases. Oops. So this is detail on how it works. Basically, the application software performs an I/O system call, which looks a lot like a Linux system call. And then all this stuff happens under the scene. There's a driver that creates an I/O descriptor. It performs a DMA operation on the node. When it completes, it just signals back to the server, and then keeps the application keeps going. So it's really nice here. It's really is just a system call, boom, on the server, and everything is kind of handled at the node level, and then the node just kind of lets the server know when it's done. And all of that happens in parallel on every node in the system. So for parallel file transfers, you just basically have a data file that you split across the SSDs on all of the node boards, so that basically whatever you're going to work on in the memory of that node, you put in the SSD. So traffic between the SSD and memory for parallel files should be all local as much as possible. And again, if it's not, the thread just migrates out into the destination node. So here it works very similarly. The application would request a parallel file transfer using one of our special parallel IO library calls that looks a lot just like a Unix call. And then the driver underneath the hood just submits descriptors to the request list at each SSD in each node. So independently, once you do that, all the nodes do all their stuff in parallel. The DMAs operate in parallel, and then all they do is they say when they're done, and they tell the driver. So it's highly, highly parallel. And the time to do all of those requests is about the same as for a single transfer, because there's very little need for communication between the nodes. So it really does scale very, very nicely in that sense. So not only do you get really, really big bandwidth on these types of applications, you also get really great scalability. And that's something we'll be delivering in the spring. So parallel ingest means you just data is coming in from the outside world over the network, and then you need to update your graph in some way with that data. Like, as I said, maybe you delete a node or a vertex, or maybe you add an edge or a vertex. So if each node has its own network interface card, you basically just give your update packet to the node that contains that vertex in the graph. And then that's just an independent operation on every node. But because we have thread migration, you don't actually need to do communication over the system interconnect. The thread migrates to the data. And then any locking that you do is done in that memory side processor. So you don't really have to stop a thread to lock it. It's done atomically at the memory side processor. So you can do lots of updates in parallel by spawning separate threads for each one. And so this is extremely powerful here. This is going to enable us to get really, really large bandwidth on parallel ingest, which is very important for like online transaction processing and such. So finally, where are we going for the future? Right, we have an FPGA implementation of this processor right now. And the reason is it's still under development. We're still scoping out the performance. So basically, the faster the FPGA, the faster we can go. So we're looking at going to next generation FPGAs with more memory and better, more advanced memory. We're looking at next generation interconnects that allow us to get 400 gigabytes per node instead of 200. And then eventually, where do we want to go with it? Well, we want to be an ASIC, right? Because that's the way to get the kinds of clock rates that are commensurate with today's architectures. Right now, our clock rate is not high because it's an FPGA implementation. Where we win is in the parallelism and the efficiency. But if we can get to an ASIC, not only do we get faster clock rates, we get lots more processing cores, and we scale the performance to even higher. So this is where we want to go in the future with this right now, which we see as an enabler for where the world is going with these graph applications. So I think that's pretty much the end of what I can talk about today, and it's a lot of material. It's really designed to sort of whet your appetite and you know, to follow up with for anything that you're particularly interested in. I can take questions now, but I think it's a lot of material, so I think I'm going to stop there.
Thank you, Janice, for the wonderful presentation. Does anyone have any questions like she asked?
Hi, just a little question. So when we are traversing the graph, do we have to go for every node and edges, node or edges for solving the problem, or we just cease whenever we have the answer?
Typically in a graph, it depends on the algorithm. Something like a breadth first search, full breadth first search means you go until you're done. You started some source vertex, and then you look at every vertex attached to that vertex, and then you look at all the vertices attached to those vertices, and you keep going until you reach the end. But something like the K-hop algorithm, you stop after K levels, where K can be like, let's say 6. So you only want to find, your 6 degrees of separation, in a sense. Like you want to find the vertices that are 6 steps away from the source vertex. So that type of algorithm. So it really depends on what algorithm that you're running. Our architecture will support whatever the problem needs it to do.
Yeah, all right, I see. Thank you.
Okay.
Any other questions? Well, if not, we can go ahead and wrap it up. And thank you, Janice, for taking the time out today to present.
Sure. Thank you so much for coming. And I can provide, my contact information. You have it. If anybody has any questions, if you think of anything, or if you want to follow up, please don't hesitate to contact me. I'm happy to go further on any one of the topics I mentioned.
Wonderful. Thank you so much for everyone for attending today.